And now on to Unit 5. This one is, I think, the most fun of any of them. We're going to be working with identities. We use fundamental identities to not only find values, but also later on here to prove some identities. We'll look at cofunctions. That'll lead us right into sum and difference. Let's see how far we can get today. We'll just do a little bit of it today. First of all, let's be clear about what is the difference between an identity and a conditional equation. You're very familiar with these. We use these a lot in algebra. We use them also in trig. A conditional equation is satisfied by some values of the variable. So if we have sine theta equals 1/2, not all, here's our variable, right? The angle. Not all angles will satisfy this, only some of them. An identity is satisfied by all. So if I had sine theta is equal to the cosine of 90 minus theta, we're working here in degrees, this is always true. The sine is always equal to the cosine of the complementary angle. So an identity, all values work. Or, actually, if you want to be really accurate here, all values within its domain. There may be some values that you can't use, and we know that that's true for some of these trig functions where we have asymptotes. Here are some of the identities that we're going to be working with. Sine and its reciprocal partner, cosecant, its reciprocal partner. These are the reciprocal identities. We have sine and cosecant, cosine and secant, tangent and cotangent. We've been talking about them all along as reciprocal partners. From here on out, I'll probably still say reciprocal partners, but we're going to be thinking about these as identities. Whatever theta is, this is also true, that 1 over the cosecant of theta. Now, there are places in that domain we can't use, right, where cosecant would be forced to be 0. So we'll go back here within its domain. So we do have that little restriction on it. Then we have quotient identities. We worked with this one here early on when we were first defining trig functions. Remember this one? We proved it. Y over R, X over R. Those are those trig ratios, right? And when we simplify this, it's Y over X, which of course is the definition of the tangent ratio. So those are the quotient identities. 2 of those. Okay, so we have 6 of these 2, and we've got another one coming up we'll talk about in a few minutes, the Pythagorean. Using reciprocal and quotient identities to solve problems. Now there are other ways we could solve this particular problem, but in this section you are to use identities to solve the problems. So to find tangent, when we know what cotangent is using identities, we're going to use our reciprocal identity, and then where we have knowledge of what this is, we put that in, then we do the calculations to simplify it, and we get our answer. So we used an identity here to solve this. In this section, you're going to use identities to do your solution. Second one, determine the quadrant that contains theta. Support your response either graphically or numerically. The cosecant of theta is greater than 0. Okay, so where is cosecant theta positive? Well, we know they're all positive here. And it is the reciprocal partner of, that's right, sine. And sine is positive here and here, so cosecant is positive in these two quadrants. Tangent theta is also positive. Well, all are positive here, and the only other place it's positive is here. So what quadrant contains theta? The first quadrant. The other way we can think about it is numerically. We can go through quadrant 1 and see what the values are for each of these. And what do we notice? As we look at this, through the first quadrant, we see that they are both positive, which corresponds to this. And then as we look through the other quadrants, we're going to see that tangent goes negative. Then in the third quadrant, when we're between 180 and 270, cosecant is negative, and over here, they're both negative. Find the other trig functions of theta. Now, using identities, we're given two, sine and cosine. Now, we would know how to figure out all of those using the ratios, but what are we trying to do here? We're going to use the identities. So for finding tangent, we can use the quotient identity. Here it is. We set that up, so there's our identity. We have a value for sine theta, we have a value for cosine theta. We put them in, we simplify it, and we have our answer. For secant, we're going to use the reciprocal identity. We have a value for cosine, and it's simple enough to plug that in and simplify. Then our reciprocal identity for cosecant, and we use the one we know, sine, and get our answer. And then, of course, we can draw on what we had up here to again use a reciprocal identity using our 12 over 5 right there to get our answer. Unit circle. We know that the sine of theta is y over r, and in a unit circle, r is 1. So with the radius being 1, here's my sine at each of the angles. That's my sine ratio. The equation for a circle is x squared plus y squared equals r squared. The equation for a unit circle is x squared plus y squared equals 1 squared, or 1. Since x equals cosine and y equals sine, we've got, instead of x squared, we've got cosine squared and sine squared plus equals 1, and we can test it. Well, we can test it? Sure. We want to verify it, right? That's what we're going to do here. So I've got all our justifications written out here. You did a lot of this work in geometry. We're just going to do a little bit more now. The Pythagorean theorem tells us that x squared plus y squared equals r squared. That's correct, eh? So x squared plus y squared equals r squared. Right up here, I'm using this. We're going to divide both sides by r squared. Then we'll have x over r squared plus y over r squared equals r over r squared. True? That will become then, let me grab it, cosine squared, that's what this is, right? Plus sine squared equals 1 squared. So we're using the Pythagorean theorem to justify the Pythagorean identity. Derive two more Pythagorean identities starting with the one we just proved. Okay, we'll do that. So we start with the one we just proved. Now if we divide everything through by cosine squared theta, now I have always recommended to my students, make sure you know this one. I think you actually already pretty much know it, but make sure that one is committed to memory, because the rest of these are easy to derive. Look how easy it is. So I end up with 1 plus, we know this is one of the quotient identities, isn't it? Tangent squared, right? And this one is a reciprocal. We can use a reciprocal identity. What is this one? Secant squared theta. Okay? And then we can do the same thing here, only this time we divide through by sine squared, and we end up with, let me write it down, I'm going to divide this by sine squared, everything I'll get, this is going to be plus 1, right? What is this going to be? Divided by sine squared? That's right. Cotangent squared theta plus 1 equals 1 over sine squared cosecant squared theta. So those are the other two Pythagorean identities. We actually have 3 Pythagorean identities. The one that you absolutely must remember is right here. Now, of course, the one we derived, I had cosine first, but we know that addition is commutative. You can put sine squared before cosine squared, and it still means the same thing. It's equivalent. So there are the Pythagorean identities. This one you commit to memory. These, yeah, memorize those, but if you forget them, you know how to get to them really quickly. Now, how about using these to solve things. If we are given that the cotangent of theta is 12 over 5, and so that we know what let me draw in what quadrant we're in. If cotangent is positive, we could be here or here, correct? We're told that secant is negative. Secant is a reciprocal of cosine. Cosine is positive here and here. It's negative here and here. So we are in quadrant 3, right? So let's use identities. We're given cotangent, so we are going to use we're going to start out with a reciprocal identity. We have cotangent, so we can figure out what tangent theta is using reciprocal identity. Now we want to figure out what secant is. So we're going to use the Pythagorean identity. The one we're using is this one right here. 1 plus tangent squared theta equals secant squared theta. All right. So we're going to rewrite that. So it's secant squared theta equals 1 plus tangent squared theta. And we'll take the square root of both sides. You remember, please, please, please remember, when you take the square root of both sides, one side is going to be plus or minus. Since we know that this has to be negative, we're choosing the minus. Okay, so that's going to guide us. This helped us figure out what to do here. So secant theta is equal to minus the square root of 1 plus tangent, which is 5 over 12, squared. Well, when you do your calculations, comes out to, I'm not going through the math here, but it'll come out to negative 13 over 12. Cosine theta, we can use a reciprocal identity now that we know what secant is. Gives us this one. So how are we doing? We had cotangent, now we have tangent. We have secant, cosine. We still need sine. Well, we could use the quotient identity here. Now I'm actually going to be looking for sine. I already have what tangent is right here. And I just figured out what cosine is right here. So sine is going to be equal to 5/12 times negative 12/13. I get my answer here. Now I'm going to use a reciprocal identity. I know what sine is. I just got it. Figure out my sixth one. So I was given 1. I knew which quadrant I was in. That helps. And then I could figure out the other 5. I had to use Pythagorean identity to do so. We can do more of these. Find the other trig functions of theta given the cosine of theta is negative 3/5 and theta is in quadrant 3. So here's another one which we're told right up front that we're looking at quadrant 3. So how are we going to figure this out? We have remember, we're only going to use identities. There are other ways we could figure this. We said we were only going to use identities in doing these calculations. We have to go up here and use an identity that has cosine in it and sine. We don't want to have more than two unknowns in our equation. We know what cosine is. That was given to us. Sine squared is going to equal 1 minus cosine squared. We take the square root of both sides. Of course, we know it's plus or minus. But since we're told it's in quadrant 3, what is sine in quadrant 3? It's minus. So we know which sign to use. Then we plug in the value we were given, negative 3/5, and we get sine. Knowing sine and having cosine, we can use the quotient identity to calculate what tangent is. Then we can use the reciprocal identity to get cotangent. Similarly, we can use reciprocal identities to get cosecant and secant. So please notice we are using identities to solve these. Whoops, I think I skipped by something. This comes out of your workbook. In this section, you're proving that trig identities are true. They are. Don't imagine that they're not. Here's an example. Can you prove this one true? Well, what we will do here is we'll focus in on only one side. So this side we're going to leave alone. We're not going to touch it. We're going to do all our work over here, and we're going to use the fundamental identities to prove this. Well, let's convert this into, let's use the reciprocal identity here. So we'll have sine theta times 1 over, well, what is a reciprocal identity for this? Cosecant is sine theta minus, we're not going to do anything to this. So we've got everything in terms of sine theta now. So I'm going to distribute sine. I'll have sine over sine, which is 1, and sine times sine, so I've got minus sine theta squared. Now I am not doing anything with this side. It's staying the same right down through. Not doing anything. What can I use here? Well, I'm going to use Pythagorean identity. Equals 1. This could be written as cosine squared theta equals 1 minus sine square theta, right? So I'm using the Pythagorean identity here to prove this. This is equal to cosine squared theta. Example 2. I've got two sides. Which side should I work with? I think this one looks like the more complicated side. Usually we'll choose the more complicated side in order to, well, this is one we'll work with. We're going to leave this side alone. So this could be written as secant x times secant x over tangent x, couldn't it? So it could also be written as secant x over tangent x. Oh, wait a second. I see a better way. You don't have to see your way through to the end to get started on these. Just get started and play around with it. I can see I've got secant x already. So secant x, I get the first part of it. And then this could be written as secant x over tangent x. And secant is let's put it in terms of sine and cosine. All of these can always be written in terms of sine and cosine. So secant is the same as 1 over cosine x. And tangent can be written using the quotient identity as sine x over cosine x. And what do we notice? That these could cancel out, leaving me with secant x over 1 times 1 over sine x. And it turns out that 1 over sine x is cosecant x. So there, I proved it. I never touched this side. I left that side alone until I could get this one to match. Simplifying expressions. We're going to be using some algebra. Didn't your algebra teacher tell you that that was going to be valuable? It's true. Multiply an algebraic expression. We're going to do that. And notice what's happening here. If I were to tell you that x is standing in for tangent theta, this starts to make sense, doesn't it? Here's tangent theta, here's tangent theta, and you notice up here, x plus 1, 2x minus 1, 2 minus 1. So do your multiplication without the trig function. It's so much easier, isn't it? But maybe it's not a whole lot easier, but it's a little bit easier. When you multiply this out, it is going to be, remember doing, what do we call it? FOIL, the first, then the outside, then the inside, and then the last. And when we simplify it all, this is what we get. So I could do the algebra, and then it makes this piece easy, because now I just take all my where my x's are and I put in tangent. So I have, instead of 2x squared, to tangent theta squared plus tangent theta minus 1. I'm going to do the same thing with this. We will use algebra first. I need to have a common denominator, which I get by multiplying the top and the bottom. I'll show it right here. X over x gives me x squared over x. Then it's x squared plus 1 in my numerator and x in my denominator. So if I have allowed x to represent tangent t, it means that this expression here, x plus 1 over x, represents tangent plus 1 over tangent. And I could do the same operation. I end up with this result, tangent t squared plus 1 over tangent t. This, anytime you see a 1 in there and something squared, think about your Pythagorean identities. Let's go back here, see if I can find the Pythagorean identities. Yeah, here we have one. 1 plus tangent square theta. Let's see if we can use it. Yes, it's just in the reverse order, but it's 1 plus tangent square theta equals secant. So you would keep going after you've done the algebraic piece of it, keep going and simplify. We're going to do another one in the same way. Here we have an algebraic expression. Now how would that relate to the trig expression below? Well, if we let x represent tangent theta, can you see how that is going to work for us? Let me put this up here. 1 over tangent theta is cotangent theta. This whole thing is in parentheses and squared. So we'll do it algebraically without using tangent and cotangent at first. If we square this, we end up with one over x squared. We end up with, let me work it out this way. I don't like what I've got here. 1 over x plus x times 1 over x plus x. Agreed? And we'll do foiling again. And when we do, we end up with, here's our first term. There's our first. And our last is right here. Our inside was x times 1 over x, which would give us 1. Our outside was 1 over x times x, which would give us another 1. So this is our outside and our inside added together. I have cotangent squared plus 2 plus, yeah, that's actually right here. I want to change my pen color. This piece here is what I'm seeing right here, isn't it? 1 over x squared, if x is tangent theta, 1 over x squared is cotangent theta squared. And here's the 2 right here. And x squared is tangent squared theta. So that's where that came from. Now, if instead of thinking of this as plus 2, I think about it as plus 1 plus 1, I can associate the cotangent in one of the plus 1s and the other one of the plus 1s with tangent. So there's that one, and there's that one. And I can use my Pythagorean identities to finish this up, right? This is equal to cosecant squared, and this is equal to secant squared. So if I write those in using the reciprocal identities now, 1 over sine squared plus 1 over cosine squared, if I want to have a common denominator, and when you have this kind of a situation, you want to get the common denominator. What happens is I multiply this side by cosine squared over cosine squared, and so my 1 becomes cosine squared theta, and this one I multiply by sine squared over sine squared, so the 1 becomes sine squared, and I get a common denominator. So I end up with this as the simplest answer I can get. Simplifying expressions. Here's a general strategy that you're going to use for proving an identity. First of all, you work with only one side of the equation. And you need to show the sequence of the expressions as you move. You're headed for 2, right? You have to show every step along the way. When the expression becomes identical to the other side, your work is done. So, step by step. Don't skip a step or you will be considered incomplete. Step by step. Start with the expression on one side, end when the expression becomes identical to the other side. The sequence of expressions, it must be easily seen that it is equivalent to the preceding expression. So we begin with the more complicated expression and work towards the less complicated. In the one we're about to do, we're going to translate everything to sine and cosine. And then we're going to combine fractions. What did we say? Anytime we have, go back here, anytime we have 2 fractions, we want to get the least common denominator. So now we're going to do an example of that. Let me guide you through what we're doing here. We have tangent, which can be expressed as, what do we call that? The quotient identity. And then we have cotangent, and we have the quotient identity for that one. So what did we just do? We expressed tangent in terms of sine and cosine, and cotangent in terms of sine and cosine. Now, we've got 2 fractions. When we have 2 fractions, we want to find the least common denominator. In this case, it'll be cosine x times sine x. So we multiply by a fancy 1, and we choose what that 1 is, depending on what was missing in the denominator. This one was missing the sine, so it's sine over sine. This denominator was missing cosine, so we're going to do cosine over cosine. We end up with these squaring. So we've got sine square x plus cosine square x. Now, this should jump right out at you as a Pythagorean identity. We're going to go back and look at that for a moment. The very first one, boy, you want to memorize this one. Sine square plus cosine square is equal to 1. You're going to see that one coming up again and again and again. So that's all equal to 1. Now I can separate this out into 2 fractions being multiplied by one another. 1 over cosine and 1 over sine, which is identical now. So we're done. Match the function, this, with one of the following. Okay, which one is a match? Is this the one that matches, or is this the one that matches? Confirm the match with a proof. You can use your graphing calculator to find out which one is the likely match. Let me show you how we would do that. How would we do that? We're going to, yeah, I've got a default window, that's good. And we'll start with this expression here. I'm going to set up y1 equal to all of this. Let me get my calculator back. So I'm going to have 1 divided by and I'm going to have 1 divided by, what's the reciprocal identity for secant? That's right, cosine x close that, and minus 1, close that. Seems like an awful lot of parentheses, doesn't it? I'm probably overdoing it. Plus, now I'm going to have 1 divided by, and we're going to go through the same process again to represent secant by 1 divided by cosine x, and this time plus 1, close that, and that. Okay. Now we're going to do a zoom trig. Oops. Go down, or say 7. Okay, so that's what that one looks like. Well, I already know that that's, oh, it's not this one, is it? Because 1 over secant x, what would that graph like? This is the same as, that's right. And that would have been a sinusoidal. So I say this one is out. I think we're going to be matching to this. All right, let's give it a try. We use the graphing calculator to see which one was likely. We say this one's likely. Doesn't mean it is the one. No, we have to prove it. Okay, so we're going to start with the more difficult side. And one of the things we're going to want to do is get a common denominator. So 1 over secant x minus 1, that whole thing is going to be multiplied by a fancy 1, and that fancy 1 is going to be secant x plus 1, secant x plus 1, and then, so I've got this one, and I'm going to do this one. 1 over secant x plus 1, and to get a common denominator, this one needs the secant x minus 1. All right, what will that simplify to? Well, I'll have 1 times this and 1 times this. That's going to be simple enough in my numerator. So I'm going to have secant x plus 1 plus secant x minus 1. And in my denominator, I'm going to have, oh, that looks so bad. Let me just fix it. Looks so bad I can't even read it, and I wrote it. When we multiply these together, if we FOIL it, we get secant squared x, and our inside and outside will cancel out. I'll have a positive secant x, negative secant, that'll give me 0. And then I'll have a plus 1 times the minus 1, that'll be minus 1. Let's try simplifying this a little bit. I'll have 2 secant x, and we'll have a plus 1 and a minus 1, so that becomes a 0. Secant squared x minus 1. Let's look at our Pythagorean identities. Keep going back there a lot, don't we? Secant squared minus 1. Well, if I subtract 1 from both sides, I've got tangent squared, haven't I? So that's the same as tangent squared x. So this could be written as let's divide it out into 2 times secant x over, and I'm going to say tangent x, tangent x. That's just the same, isn't it? I gotta put the multiplication there. Does that look just the same? The reason I've done that is because it occurred to me that with this one, I could now rewrite this as 2 cotangent x. The only problem I have is how do I get to cosecant? If it isn't obvious how to do that, write it out in terms of sine and cosine. How can I write this in terms of sine and cosine? That'll be 1 over cosine x, and tangent will be am I getting where I need to get? I hope so. Tangent will be sine x over cosine x. And then these will cancel out, and I'll have 1 over sine x, which is the same as I think I've got it. Ugh. All right, done. Well, they take some time. They're not quick. Here's another one. I'm giving you so many examples. General strategy for proving, oh, that's the one I just did. It's done. All right, here's a new one. We want a new one. We can use the algebraic identity. Remember this one? The difference of squares. We have the conjugates here. A plus b times a minus b will always yield difference of squares. It's going to be very useful when you're working with Pythagorean identities. Keep in mind what you're headed to. That would be probably this one. I'm going to work with the left-hand side and leave the right-hand side alone. All right. So I'm not going to touch this. This is what I'm headed to. I'm just going to work with this one and see if I can figure out a way to go from here to there. And now notice I'm starting by multiplying by the conjugate. And when I multiply these together, the conjugates together, what do I get? I get a difference of squares, 1 minus sine squared t, which I know is, with the Pythagorean identity, is the same as cosine squared t. Remember that one? This is the one I'm asking you to commit to memory. You can always derive the other two Pythagorean identities. Just make sure you know this one. And if you do, it occurs to you that if you subtract sine square from both sides, 1 minus sine square, you can use cosine square here. And once I've done that, what do you notice? Well, I can cancel out this with one of those, and I end up with the expression I was headed for. Here's another one for us to practice with. You might want to work from both sides. Sometimes it's not clear how you're going to get there. If you can figure out how to get to an intermediate expression, then you can work it all the way through to the end. I'm going to show you an example of what I'm talking about. So in this one, when I looked at it, I thought, oh, I don't know. I don't see how I'm going to go here. So I thought, well, I'll work with this a little bit and see what I get to. And then I'll work with this a little bit and see what I get to. So what did I do over here? Well, I recognize that this expression down here could be part of a conjugate pair, and this could be factored into conjugates. Very good, because when I do that, I'm able to cancel that out. So I could get to there. On this side, I couldn't see what to do, so I re-expressed everything in terms of sine and cosine and looked for a way to simplify that. And I saw it because when I multiply these together, the cosines cancel out and I end up with 1 over sine u. When I multiply these together, they become 1. So now I can see my whole path. I don't have to touch this side. I can leave it alone, and my path will go from there to there, and then to there, and from there I'll go there, and there, and then I will be done, right? Because I've proven it. So sometimes you might work from both sides to get to something common in the middle, which will give you a link to find the whole path. Now this is just showing that being done. So this just is what we looked at a moment ago. General strategy for proving an identity. Begin with the more complicated expression. If you don't see what to do, translate everything into sine and cosine. You can always do that. Put things over a common denominator. Don't forget about conjugates, because these Pythagorean identities, they can use this algebraic identity a lot. Be aware of what you're headed to. Work from both sides if you need to get yourself an idea of how to get there. Do not be discouraged if you don't have much of an idea of how to do it. Just get started. Do something. Wow, this is a long lesson. This we're going to have you do back in class, okay? 58 minutes. Wow.